if you've not been here, let's see, on, I don't know, Thursday, Friday, Monday, Tuesday, Wednesday, I don't even know what days anymore. Then here's what you need to know. I left off talking about this stuff here and how to sketch these particle diagrams for the lab. Now, if you weren't here to even collect the data for the lab, you should at least know what your classmates did, because there is a printout or a PDF file of the actual lab on Classroom that tells you what exactly you were supposed to have done, measuring the mass of 4 different parts, because we didn't do the ice water part. So parts 1, 2, 3, and 5, that's all on there. You can read that and see what you were supposed to do. Now, for the I lost my train of thought. It'll come back to me. Just a second. For the particle diagrams of each of the 4 parts, I had briefly mentioned, again, I had like some diagrams, some sketches like this that were in the video, the last video. So I'm going to talk a little bit more about those, and then tell you what we talked about basically today, which is Wednesday, which is B1. Yeah, B1 day on Wednesday. So if your steel wool stayed the same mass, then in your after picture, I'm assuming, you're going to have the same number of particles, but you will probably draw them spread apart, further apart from each other, because that's what you did. You literally, for the steel wool stretch, SWS, for the steel wool stretch, you fluffed up the steel wool, puffed it up twice its size. But if the mass didn't change, then you have the same number of particles, they're just further apart. That's how I would think you would sketch it. If your mass went down for that, so before it was maybe 0.28, after it was maybe 0.26 grams, then while you would draw them further apart, you would also draw fewer of them to indicate to those looking at it that you lost some mass. Now, the explanation that some folks gave in class was that some fibers fell off. When they fluffed it up, the fibers fell off, and a couple fibers falling off means there's less of it, which means your mass was less, and so we just draw fewer particles. Now, some folks had the mass go up. Now, I don't know how exactly you describe that. That's a tough one. How did fluffing the steel wool make the mass go up? Which means there's got to be more particles there after than before. Well, more particles of what? Like, did you gain steel wool when you fluffed it up? Is there more steel wool there after you fluffed it up than before? Well, that doesn't make sense. I mean, you didn't add more steel wool to it. So where could it have come from? Well, some folks suggested that because some groups were doing the sugar and the Alka-Seltzer part, which involved water, while other groups were doing the steel wool part, that maybe there was some water on the scale that your steel wool picked up on the first measurement. And then on the second measurement, that water is still there, and then you masked it. And so maybe there are some water particles on the after measurement that weren't there on the first measurement. Well, that's the only reasonable explanation I could think of. And so maybe on the after picture, if your mass went up, you not only have all of your steel wool particles, you may also have a couple of water particles in there that you didn't know were there, but have to be because your mass went up. That seems to be the only logical reason why your mass would go up. So that's what we spent most of Monday and Tuesday. We spent most of Monday and Tuesday talking about that. Talking about how can you explain why your mass went up, why your mass went down, or why it stayed the same. Now the sugar, almost everyone had the mass go down for the sugar. Almost everyone. And the common consensus was that most people, when they were trying to pour the sugar out of the cap and into the vial, that you lost some sugar. You spilled the sugar. Well, that means then in your after sketch, you should show what? Hopefully, you're thinking that the cap, or I should say, if you drew 1, 2, 3, 4, 5, so I had 6 sugar particles in there, and if not all of them made it into the water, then maybe you would draw a couple of sugar particles outside the vial that never made it in. That would indicate that you have less mass now because not all of your sugar particles went in. You spilled some. Well, that makes sense. Some folks said that when they put their sugar in there, they think they got pretty much all of it, but then they put their cap on and that they had a hard time getting the cap to actually go on tightly because there was so much sugar still in the cap. It was kind of crunching as they put the lid on, and then they started shaking it up, and then water started coming out. Well, if water started coming out of the vial with the cap on it, then you probably should, in your after picture, draw fewer what? Water particles. So you lost some water particles, so there's less water particles in your after than in your before. So those are the kinds of things we were looking at. The Alka-Seltzer, though, the Alka-Seltzer was a little different. That one had some fizzing and foaming going on, and so every student had the mass go down. Every group out of all the classes had the mass go down for the Alka-Seltzer. And the most common reasoning there, so if we just pretend that this is now not sugar, but it's an Alka-Seltzer tablet, and then you put that in there, what happened was gas was forming. Students were saying that all the fizzing and bubbling, maybe the gas that was forming got out of the vial because you left it on loosely, which is what it said in the directions, leave the cap on loosely. And so maybe these gas particles left. Well, here's the thing. In the before picture, are there any gas particles here? No, you have water particles, you have Alka-Seltzer particles. So where do gas particles come from? Well, some of these Alka-Seltzer particles dissolved in the water. So some of those particles are still there. Some of them aren't there because when they hit the water, they became a gas and leaked out. So you will need a third particle, so not just the water and not just the Alka-Seltzer floating around in the water in your after picture. You may also need some gas particles that got out of the vial. So you would draw a third kind of particle, and in your key below, you would show this is a gas particle, and it got out. So those are some ideas about the particle diagrams and how we would draw them to show whether the mass went up, whether it went down, or whether it stayed the same. So that's hopefully maybe that helps some of you figure out like what we were doing. For the steel wool burning one, the heated steel wool, some groups had the mass go up, and we said, well, I wonder if there's something from the flame that deposited itself on the steel wool that wasn't there before. And so in those cases, if your mass went up for the steel wool heating part, maybe you would draw a second kind of particle on the steel wool that wasn't there before, and then label it like unknown particle from flame. I mean, I don't know what you would call it, but that's the only thing you did differently. You took the steel wool, you masked it, you put it in the flame, you masked it. If it went up, the only logical explanation is that the flame put something on the steel wool. Those that had the mass go down for the steel wool burning part said that some little fibers got burned up and came off. Well, that makes sense. So you would draw less steel wool after because some of it got burned up and removed from the steel wool. So anyway, that's that one as well. Now, we switched gears from that and we talked about what the big idea was. And so here's the big idea. The whole big idea of this mass and change lab, is that All matter is made of particles. Okay? And the measure of how much stuff or the number of particles is called mass. So write that down. Pause it. Write that down. This is like notes. Okay? So this is the big idea of the lab and why we did it. Then we went on to say this. There's this thing called the law of conservation of mass. Again, if at any point you're not getting all this, then pause it, write it down, and then come back and keep watching it. The law of conservation of mass says this, and some of you may already know it, that the mass of a closed system will remain constant. The mass of a closed system will remain constant. Now, in the lab, very few of you had the mass stay the same before and after. Very few had the mass stay the same. Most of you had the mass change. So does that mean the law of conservation of mass doesn't work? I don't know. So in other words, what this law of conservation of mass says, you can't create or destroy particles. The particles, you cannot create or destroy them. We can rearrange them, but we can't create or destroy particles. Now, if your system mass changes, so again, the law of conservation of mass says the mass of a closed system remains constant. It doesn't change. Then what if the mass of the system changes? Then what? Like, how do you explain that? How do you explain that the mass of the system changed? Well, that means that particles either left your system or came into your system. In other words, it must not be what? It must not be a closed system. So if you had particles that left or came into, you have an open, not closed system. So in our 4 situations, we had the steel wool where you stretched it. We had the steel wool where you heated up in the flame. We had the Alka-Seltzer, or we had the sugar in the water in the cap and the vial. And then we had the Alka-Seltzer in the cap and the water in the vial. Were any of those sealed, closed systems? No, they weren't. So particles could easily leave or come into the system without you knowing it. So you had open systems. Can the mass change in an open system? Yeah. And that means particles came into or left. But if the system was closed, then the mass shouldn't change. Now, I showed this. I took the Alka-Seltzer. I took an Alka-Seltzer tablet, a vial, the cap, and the water. I masked it all. I dropped the Alka-Seltzer tablet in there, and I put the cap on as fast as I possibly could, and I cranked it down tight. And you know what happened? The mass didn't change. The mass stayed the same. Because what did I do? All that gas that was forming, I didn't let it out. I capped it tightly. And so I went from an open system like you all had, and I went to a closed system here. I made it closed by capping it so that nothing could get out. The mass stayed the same. And then what do you know? I uncapped it, and we heard all that gas in there, the pressure that had built up, it got out. And when I masked it, what do you think happened? The mass dropped. So, does a gas have mass? Yes, because it's made of what? All matter is made of particles. And the measure of how much stuff or how many particles there are, that's called mass. So, by venting the vial, when I took that vial that we used in class and I uncapped it, that gas got out, which means I lost some particles, which means I lost some mass. So I went from a closed system with the lid literally closed to an open system where I let the particles out and then my mass changed. Hopefully that makes sense. So if your mass changes, it's because you have an open system and particles either came into it and the mass went up, or they left and the mass went down. Now, what else is here? I forget what else is here. Oh, During this little lab situation, we had two kinds of changes, right? There's two kinds of changes in matter. Now, this does not affect whether there's an open or a closed system. It does not change the fact that there is this thing called the law of conservation of mass. That's still a thing, regardless. But I'm telling you that of the four things we did in class for this mass and change lab, there's two kinds of changes that we saw. One, hopefully you're thinking of what these changes are called. One's a physical change. During a physical change, you have the same substance. You're not changing substances. It's the same stuff that's there. All right. Now, examples would be things like cutting, smashing, melting, dissolving, boiling. I should have said freezing, etc. Those are the kinds of things that are physical changes. Does the mass change during dissolving? No. Does mass change during melting? No. Does cutting or smashing or boiling, does that change the mass of something? No. If it's a closed system, the mass will remain constant. If it's an open system, then you're going to lose particles, possibly, or new particles will come in. This has nothing to do with the law of conservation of mass. Like when you melt something, the particles don't just go away. When you dissolve something, particles don't just go away. They're still there. But it is a physical kind of change. When you dissolve the sugar in the water, the sugar is still there. It's just really spread out in the water. Instead of being in a little crystal, all concentrated so you can see it, it's spread out to where you can't see it anymore. Now, if you put enough sugar in water and dissolve enough sugar in water, the water will start to get hazy where you can start to see that there's something in there and not just pure water. But these are all physical changes, okay? Now, there's another kind of change called a chemical change. During a chemical change, new substance forms, right? New substance forms. Now, what are some evidences of a chemical change? Well, the evidence of chemical changes, one of the evidences is fizzing and bubbling. If fizzing and bubbling is happening, that means a gas is forming. It may be a chemical change. Now, here's the thing, may be. Not every time you see fizzing and bubbling is it a chemical change. Like when you pour some soda in a glass and it fizzes and bubbles, does that mean that the soda is experiencing a chemical change? No, it means that there's carbonation, there's carbon dioxide dissolved in the liquid and then it comes out in gas form and it bubbles. That's not a chemical change. That's gas physically coming out of a liquid. But the Alka-Seltzer tablet, you took a solid tablet, you threw it in the water, and it started to fizz and bubble. That was a chemical change. A gas formed. A gas that wasn't there before is now forming and releasing. That's a chemical change. Now, does the mass change during a chemical change? No, not in a closed system. When I had the cap on tightly, the mass didn't change. It was only when I vented it, I let the particles escape, then the mass changed because it was an open system, not because it was a chemical change, but because it was an open system. See, some of you had your steel wool mass change when you fluffed it up. Not because physical changes caused changes in mass, but because you lost some fibers. You weren't careful, you lost some fibers of steel wool, and the mass changed. So again, the physical change versus chemical change, it's not a one causes changes in mass and one doesn't. Okay. You can have changes in mass occur during either of those if your system is open. I hope this is making sense. Okay. So again, I'm not saying that during chemical changes, mass changes, and during physical changes, mass doesn't change. That's not what I'm saying. I'm saying that mass shouldn't change in a closed system, period. If it is changing, then you have an open system and particles came into or left that you weren't aware of. Moving on. The next evidence would be an odor. If an odor is produced, then that's probably a chemical thing. When we put the steel wool in the flame back there in the room, there was an odor. I noticed it. People were noticing it. They're like, that stings. So if an odor is produced, that may be evidence of a chemical change. Not always, but it can be. When you bake a cake, is odor involved? When you bake a pizza, is there an odor? Or baking bread? Anytime you bake something, there is a chemical change happening. The dough or the batter or whatever it is you're baking is becoming something different. Like the crust of a pizza is not the same as raw dough. Cake batter is not the same as a cooked, baked cake. Different substances. Odor. Color change. The steel wool actually changed colors when it was in the flame. So there was an odor and there was a color change. So what happened to the steel wool was probably a chemical thing, not a physical thing in the heat. And I think this may be the last one. Yes, production of heat and light. So production of heat and light is also an evidence of a physical or a chemical change. Excuse me. I'm having trouble talking today. Golly. All right. Oh my gosh, this is so long. We're not quite done. There's more. Seriously? Yes, there's more. So now we're going to talk about what the next lab is going to be. The next lab is a volume lab. So how do we describe what volume is? Volume is how much space something takes up. Maybe I should make this a different video. I'm going to make this a different video.